in this lecture, we'll begin our discussion of Jordan Canonical Form. And the way that we're going to start is by talking about the elementary divisor decomposition of a finitely generated module over a PID and relating it to the invariant factor decomposition. So let's go back and recall Theorem 6 from section 12.1 from the very end of Math 206b. Let's say that R is a PID and M is a finitely generated R module. Then M is the direct sum of a finite number of cyclic modules whose annihilators are either 0 or they're generated by powers of primes in R. So what does that mean? We see that M is isomorphic to R to the R, direct sum R mod the ideal generated by P1 to the alpha 1, direct sum plus 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 R mod the ideal generated by PT to the alpha t. Where this little r here is the free rank is some non-negative integer. And P1 to the alpha 1, P2 to the alpha 2, up to PT to the alpha t, these are positive powers of not necessarily distinct primes in R. So because the important thing here is the ideal generated by these prime powers are only defined up to multiplication by units in R. If you take one of these and multiply it by a unit, you're getting the same decomposition here. And these prime powers are the elementary divisors of the module M. So remember, how did we go from our invariant factor decomposition to our elementary divisor decomposition? The proof of this theorem, assuming the invariant factor form for a finitely generated module over PID, was pretty easy. So what does the invariant factor form look like? We have M is isomorphic to R to the R, direct sum R mod the ideal generated by A1, direct sum plus 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 R mod the ideal generated by AM, where these AIs are non-zero, non-unit elements of R that satisfy these divisibility relations. A1 divides A2, A2 divides A3, and so on. So what did we do is we took each AI and we factored it into a product of prime powers in R. Once we have A1, for example, as a product of prime powers, we can apply the Chinese remainder theorem for modules to this quotient and get something that looks like this. So what does this all say if we're in the situation that we've been focusing on so far in this course, where V is a finite dimensional vector space over a field F, and T is a linear transformation from V to itself that gives V the structure of an F bracket X module, where this linear transformation T is giving the action of X on V. Well, OK, so we know the invariant factor decomposition of V says that V is isomorphic to F bracket X mod the ideal generated by A1 of X, direct sum plus 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 F bracket X mod the ideal generated by AM of X, where this A1 up through AM are monic polynomials of degree at least 1, satisfying the divisibility relations A1 divides A2, A2 divides A3, and so on. So once we suppose that these polynomials are monic, they are uniquely determined by this decomposition. You don't have to worry about this like multiplication by units in R. So we want to do the same thing where we go from invariant factor decomposition to elementary divisor decomposition. So the idea is to take each one of these monic polynomials and factor it as a product of primes in F bracket X. But what are primes in F bracket X? In F bracket X, irreducibles are prime. That your prime, if and only if you're irreducible, the prime elements are exactly the irreducible polynomials. So each one of these AI of X's factors uniquely into a product of irreducible polynomials in F bracket X. But because AI of X is monic, it factors uniquely into a product of monic irreducible polynomials in F bracket X. So I'm going to pause and erase and see how this observation that we can factor each one of these invariant factors into a product of monic irreducible polynomials of degree at least 1 in a unique way takes us from the invariant factor decomposition to the elementary divisor decomposition of our F bracket X module V. We have our invariant factor decomposition of our F bracket X module V. And just like to prove the elementary divisor decomposition theorem in general for a finitely generated module over a PID, what we want to do is just factor each one of these invariant factors into a product of powers of prime elements in f bracket x. So we're going to get each one of these factored as a product of monic irreducible polynomials in f bracket x. We're going to group together the terms corresponding to the same factor. So before actually factoring, let's also note that if you take the product of all of these invariant factors, that's something we know. That's the characteristic polynomial of t. So ct of x is the product of these irreducible factors. And what are the roots of that characteristic polynomial? Those are the eigenvalues of t that are in f. So now we're going to make an assumption that's really important for this section and the discussion of Jordan canonical forms for matrices. We're going to suppose that f contains all of the eigenvalues of t. So why is that an important assumption? Because the roots of the characteristic polynomial are the eigenvalues of t that are in f. So if all of the eigenvalues of t that are in f, if all of the eigenvalues of t are in f, then that means each one of these invariant factors is going to factor into a product of powers of linear polynomials. So all of the eigenvalues are in the field. So we're going to get exactly the number of roots that we'll get when we factor the right-hand side will be the degree of this polynomial. So we're going to get each invariant factor factoring into a product of powers of linear polynomials. So what does that look like? So if a of x, this is just standing in for some invariant factor, ai of x, this is a product of x minus lambda 1 to the alpha 1. Lambda 1 would be our first eigenvalue of t, and alpha 1 will be the multiplicity of that eigenvalue. And then x minus lambda l to the alpha l. This will be our last eigenvalue, and it occurs however many times. By applying the Chinese remainder theorem for modules, we saw that this implies, if you have this factorization, you get that f bracket x mod the ideal generated by a of x is isomorphic to this direct sum of f bracket x modules, f bracket x mod the ideal generated by x minus lambda 1 to the alpha 1, direct sum plus 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 f bracket x mod the ideal generated by x minus lambda l to the alpha l. So what are we seeing? We're seeing that v is isomorphic to a direct sum of finitely many cyclic f bracket x modules of a very particular form. They're of the form f bracket x mod the ideal generated by some linear polynomial raised to some power. So what are we doing? We saw this for one invariant factor. We just apply it separately to each. We get each invariant factor as a direct sum that looks like this. We just take the direct sum of all those direct sums. And this form is the elementary divisor decomposition of V. So once we knew that we had this invariant factor decomposition of V, the next thing to do was to choose a good basis for each one of the pieces in our decomposition such that we get a corresponding basis of V for which the matrix of T with respect to that basis has a particularly nice form. For invariant factors, this led to companion matrices and the rational canonical form. When we go through the same process here, this is going to lead to Jordan blocks and the Jordan canonical form. And we'll start that discussion in the next video.